what the study is about in broad terms is to look at and to quantify what the effect on emissions would be globally of population changes of various kinds. And that includes not only population growth and decline, or changes in population size, but also other demographic factors such as aging and urbanization and their effect on emissions as well. And the reason this study is new, I mean, the idea of saying, hey, population might affect emissions, let's see how big that effect might be, as you can imagine, is not new, right? There's been work done of this kind before. What's new here, I think, is one is I think that this is a better quantification of that effect for a few reasons that you'll see as we go through the talk. So I think we're on a little bit firmer ground than in the past on what the size of this effects might be. Second is that it does go beyond population size to look at some of what we call these compositional changes in the population, not just how many people there are in different parts of the world, but what types, urban, rural, young, old, and so on. Third is that we're accounting for interactions between population changes and the economy. And while different studies have looked at pieces of this story, the effect of aging, for example, or demographic changes in one part of the world, this is really the first time that I know about that all of these different pieces have been put together into one analysis to look at, when we consider all of this together, how much does it matter to emissions globally when you add it all up if you follow a slower population growth path rather than a faster one. So the study design is a lot easier to describe than it was to carry out. But in principle, it was pretty straightforward. We adapted an existing model of the global economy, energy system, and carbon emissions of the kind that is typically used to develop long-term emission scenarios for doing climate change research. And we further developed it to make it, to add the capability to handle demographic change in a more sophisticated way than has been done in the past. Second, we had to put together and to some extent develop some long-term population projections that include all of these various dimensions, urbanization and aging and changes in living arrangements like household size, over the next 50 to 100 years, and then put the two of these things together to say, well, what happens to emissions in different parts of the world when you change your assumption about the population path that the world will be on from one path to another. So I'm not going to go into any details at all about the model. You'll be thankful to hear. But just so that you have a general idea of what we're doing here, the model is global in coverage, but it breaks the world up into 9 different regions, which are shown here. 3 of those regions are individual countries, so China, India, and the US are their own regions. The other 6 are aggregates of a number of countries. The regions interact through trade, and the model is modeling the economy and economic growth and the link between economic growth, energy use, and emissions in each of those regions. Within each region, the population is further broken down by these demographic dimensions that I've mentioned. So within each region, we're differentiating the behavior of urban households from rural households, older from middle-aged or younger, and households that have more people living in them from households that have fewer people. The population projections that we're using, the way we designed the study was to look at 3 different possible, plausible population futures for the world. This graph shows the global total population size in these projections. The middle one, this blue line, is our central sort of medium case. All 3 projections come from the United Nations. And in this medium projection, you see that the world starts off, well, say 2010 is just below 7, as Lori said, it's just below 7 billion today, and in the medium case levels off around 9 billion by the second half of the century. In the low scenario, global population reaches about 7.5 billion before starting to decline to below current population size in the long term. And in the high scenario, population grows faster, so by the middle of the century, we're around 10.5 billion and still rising. So the way we're structuring our analysis is we first produce an emission scenario, assuming that population follows this medium path. And that's kind of our base case. What we really want to know is then, how much do emissions change when we substitute either the high or the low population growth path for the medium? Now we can also look at, as I mentioned, we have 9 regions in this analysis, so population growth is proceeding differently in all of those 9 regions. So we can also say, let's take a look at the difference between the medium and the high, this global population difference, and see which regions are actually accounting for that difference. So all of these colored bands here show the contribution to the global difference in population size that comes from each of our 9 regions. So really the only one thing I want to emphasize from here is that the kind of white, tan, purple shades are the currently developing country regions. The 3 greenish bands at the top are the industrialized country regions, US, EU, Japan, Australia, and so on. So you can see that only a very small part of the difference in global population size is due to population in these regions, something that is well known. By far, the global population size will be determined by how population growth turns out in developing country regions. So we take these projections, they include aging, we combine them with urbanization projections, we combine them with household projections and household size, and run them through the emissions model, and let's look at what we get. So here's the same kind of graph that we just looked at, except it's total carbon emissions rather than total population. And here's our global emissions result. The blue line is global emissions, and we're calling this the B2 scenario. It's designed after a well-known scenario in the climate change literature that happens to be called the B2 scenario. That's our version of the B2 scenario with medium population growth globally. What we're really interested in is how much does that blue line change when we switch the population assumptions, and those are shown by the 2 red lines. So if we look at how different are they, let's just take the example of the high emission scenario, the scenario with high population assumption versus the medium. We find the difference is about 1.7 billion tons of carbon per year in the middle of the century. If you follow the high, you've got that much more emissions per year than you would if you were following the medium. As Laurie said, that's equivalent to about 1 wedge of carbon emissions in this wedges analysis. So if you were to move from the high to the medium, you would save 1 wedge of emissions. And in that Princeton analysis that she showed, roughly speaking, you needed about 7 wedges of reductions to be on the path to avoiding the worst climate change outcomes. So this shows that moving from the high to the medium can get you 1/7 of the way there. In the longer term, of course, the effect of population is much bigger. It's a really significant effect on long-term emissions. The effect of population, the population size differences accumulate over time. So the farther you look out into the future, the more difference this actually makes. Now, again, we can look at where in the world are these emissions reductions coming from. We color these the same way. The only thing I want to point out here is now the green bands are a lot bigger than they were in the population curve. And that's because, as Laurie has emphasized, emissions per capita in these industrialized country regions are substantially higher than they are in developing country regions. And so the small difference in population makes a big difference in, a bigger difference in emissions. Most of the emissions difference is still from the purple and tan areas. Now that also accounts for the flip side of the coin, right? Per capita emissions in those regions are lower. They are lower in this model, but they still add up to a lot of emissions reductions for 2 reasons. One is that those per capita emissions are rising over time. They don't stay low forever. And second, the differences in population outcomes are much bigger, as we saw previously, in those parts of the world than they are in the industrialized country regions. So actually, population changes matter in both regions. Finally, take a look at, well, what about this aging and urbanization stuff, right? Okay, so you put in all these extra things. Do these things actually really make a difference by themselves? Now, if we just want to look at, now we're not looking at the difference between two population scenarios. We're just taking our medium population growth emission scenario and saying, what is aging and urbanization doing to emissions in that scenario? If we add this up over the whole world, in 2050, aging is pushing emissions down by about 500 million tons of carbon per year. By 2100, it's close to 1 billion tons, reducing emissions relative to what emissions would be if aging were not occurring. So the fact that we're taking it into account is actually pushing emissions down. This happens primarily because older households are not working as much. Because there's less labor in the economy slows down, and the overall energy use goes down and emissions go down. So this illustrates the importance of taking into account some of these interactions with the economy when looking at demographic change. Urbanization works in the opposite direction. We find that by 2050, urbanization is increasing emissions by 0.5 to 1 billion tons of carbon, and by the end of the century, it's getting closer to 1.5 billion tons of carbon increased relative to ignoring urbanization. And it's for a similar reason. With urbanization, urban households contribute more to economic growth. Urbanization drives economic growth and therefore energy use overall.
What about migration?
We'll come back to that, yeah. This shows exactly the same results but broken down by region rather than adding them up for the world. The point here is just that urbanization doesn't matter everywhere. It matters a lot in some regions. Here, for example, China and India is very important to emissions outcomes, not so much in other regions like the US and the EU because we're largely urbanized already. Aging, the blue bars, is important in industrialized country regions in general and also in China where aging is happening as well. So to sum up, so we find on the population growth side that slower population growth wouldn't solve the climate problem, as Lori said, but it could make a contribution. This is my own little metaphor here. So we find it's neither a silver bullet nor a red herring. It is somewhere in between. It took me a long time to draw those things, so I hope you know what they actually represent. Urbanization and aging are important things, important factors to determining emissions outcome in some parts of the world. What does this all mean for policy? I'm going to postpone that question to the discussion sessions. I'm sure there will be plenty of ideas on that from everyone.